it's 6 p.m. So I will wait for a couple of minutes and let people join. Otherwise, I will start the session after a few minutes. Okay, since this will be a quick 1 hour session, so I don't want to wait for more. I just want to start the session. People can join in the middle as well. So let's start the session. So, hello everyone, welcome to the live session for the course Sensors and Actuators. So, this is not a regular live session that we have on Tuesdays, but this will be an extra session. So I'm taking this to like I will try to give you the summary of this course, although it is not possible to give a summary in 1 hour for a 12 weeks course, but I will try to like this will be like a revision for all the topics that we have discussed, and the topics those are the important topics, I would say, and we spend significant amount of time in these topics, so that those topics I want to revise in today's session, and I will also give you questions related to those topics, and we will solve the questions together. Okay, if you are watching on YouTube, then try to solve the question, give answers along with me. Try to do it along with me, and this will be helpful in your final exam as well as for assignments. So, if you are new, if you are watching this live sessions for the first time, then let me introduce myself first. I am Ananya. I am a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI, and I did the live session for this course, Sensors and Actuators. We only have 1 week left. That live session will be on next Tuesday, and in the live sessions we try to uh, solve few questions. Along with that, I also uh, give brief overview of the topics those are covered. So generally start the session with a brief overview so that everyone is in the same page, and that is like a quick revision, and then we can start the questions. Okay, so we will do the same thing in today's class as well, but this is an extra session. We will try to cover as many topics as possible. Those were the topics that we already discussed from week 1 to week I won't do probably week 11 because that was just few days back, and week 12 obviously we will do on next Tuesday. So from week 1 to 10 I will try to summarize everything so that this will be for your reference. So the topics those were covered in week 1 and 2. So these are the topics. So first thing we discussed in week 1 and 2 is that like some basic terms. We learned about some basic terms. So first one is what is a sensor. So the definition is it is a device that can measure some physical quantity. That can be say temperature, that can be pressure or something, right? It measures some physical quantity. The output can be electrical, it can be optical. Okay, so the output of a sensor can be electrical. Okay, electrical can be like a change in resistance, change in voltage, something like that. Optical, it's a change in color. So we know, we had discussed about many biological sensors that can change color depending on whether certain analyte is present or not. Okay, so the output can be optical, can be mechanical. So this one example that we discussed is that mechanical output is like say your output is as form of an output. You have a pendulum and it is moving like with a certain frequency, and the change in that frequency that can describe something. Okay, so the point here is that the output of a sensor should be like a readable, it should be in a readable format so that people can understand whatever change is happening in the physical quantity. The output reflects that in some readable format. By readable, I'm not saying that it should be written, but at least we can see and like identify that something is different. Okay, the physical quantity change. Next definition that we learned is actuators. Okay, so these are responsible for some movement uh, in the system, or some parts of the system, right? So what an actuators can be, it can be like a valve. Okay, example can be a valve that will open or close, and then there can be stepper motors and all these things that can move something from one place to other. Okay, we have also learned about the basic block diagram of a sensor system. So sensor is like, we will have sensor, then there will be some decision making unit, and there will be actuators. Sensor will sense something, so I'm just writing decision making unit. The sensor will sense something, some physical quantity. Based on that, we will decide something. Okay, and that based on that decision, actuator we will provide some input to the actuators to do something. Okay, this is the basic block diagram of a sensor system. Now, what kind of sensor we will be using in our sensor system, that depends on the requirement and the applications. This is also we have learned that there are certain factors like what are the sensor characteristics. The characteristics can be like sensitivity of the sensor. Another thing can be like a response time of the sensor, and can be the range of the sensor. Okay, say it's a temperature sensor, it can sense a temperature in the range, say 10 to 100 degrees Celsius, then that will be the range of the sensor. We decide a sensor based on these things, as well as the environmental conditions. Say if we want to use a sensor at a very high temperature in an industry, for some application in the industry, then we will use a sensor that can sustain that kind of temperature, right? And also we will look for economic part of it. We don't want to, suppose in case of an IoT, Internet of Things, so that requires many sensors. We will always go for a sensor that does not cost much, and many times, but what may happen, like the lower cost sensors may have like a does not have very good sensor characteristics, maybe like a very low sensitivity. But if that works uh, in our application, for our application, then we will obviously go for the lower cost one. Okay, if we have to choose between two sensors. Now, uh, this we have learned that while choosing a sensor, it how we will choose it depends on the requirement and application. We will consider the sensor characteristics, we will consider the environmental conditions where it is going to be used, we will consider the economic factors. Okay, these three things we have learned. And then also we learn that the sensor technology, this subject itself is a multidisciplinary subject. It requires knowledge of many areas. For example, if you are working in a biological sensor, then you will need the knowledge of biology. You will need the knowledge of electrical engineering if you are making electrical sensor. Okay, and then you have to have the knowledge of fabrication, some material aspect as well, if you are actually making the sensor, fabricating the sensor. So who people have joined now, so I have just given the introduction. So this is an extra session, as I mentioned like earlier, live sessions also. So this is not particularly for any week, so we are just discussing like whatever content that we have learned throughout this topic. So this is like a quick summary of the things that we have discussed from week 1 to 10. I'm not covering week 11 that we just discussed few days back, and for week 12 we will have another regular session on Tuesday. Okay, so I'm just trying to give you a summary of everything. Okay, so these are the things we learned in week 1 and 2, and in week 2 we have also discussed about VOC sensor. So VOC stands for volatile organic compound. What are volatile organic compounds like acetone, ethanol, all these things. And we have also discussed VOC sensors for human blood analysis, how we can detect diabetes, a person with diabetes using a VOC sensor. We have also discussed how VOC sensors can be used, ethanol sensor can be used for to detect like alcohol and to prevent drink and drive cases. All these things we have discussed. And then we also briefly discussed about e-nose. E-nose is electronic nose, and basically using a sensor system which is like a combination of sensors and decision making unit. We try to make mimic biological organs like nose, right? So for that we will need multiple gas sensors, because our nose can sense multiple things together. Okay, our brain can process multiple things together. So this is generally a set of sensors along with a decision making unit that will decide that okay, this gas is present, say this percentage of the concentration is this much. So this kind of decision that electronic nose can make. And we have also seen that this will be very useful in case of some industrial purpose. Say I have discussed in the initial few weeks how we can actually use this kind of a sensor system. For example, one of like when I did MTech, during that time I learned that one of my faculty member there. So what he made a patent uh, that is similar to like he knows, and that can detect the quality of tea leaves, okay, without any intervention of any human being, or requirement of any human knowledge. There are sensors that can detect the quality of tea leaves. Okay, so using like a set of sensors, we can mimic certain biological organs, different organs, and that we have learned. And then we have also briefly started the discussion. We have been discussing these topics regularly. So what are the deposition techniques? So as I mentioned, in microfabrication there are like four components. One is deposition, one is lithography, and then another is etching, and then the last one is doping. So we started with the deposition techniques, and we learned that there are two types of deposition techniques. One is physical, one and another one is chemical. As the name suggests, in physical one we use physical force to deposit a material. And what are the physical vapor deposition techniques? Sputtering and evaporation. And chemical deposition techniques, so these are the techniques where we use chemistry to deposit a layer. And the examples of chemical vapor deposition techniques is CVD, chemical vapor deposition, ALD, atomic layer deposition. Okay, so these things we have studied in week 1 and 2. So let's take a question. So this is just I am trying to give overview of 1 or 2 weeks, and then one question that we discussed during that time. Okay, so the question is, what are the advantages of microfluidics? Okay, so the options are: it can mimic the complex fluidic system, in a lab setup. Option B is fluid flow can be controlled more easily. Option C is these are cheaper. Okay, cost is obviously one factor when we decide a sensor. And last option is all of the above. So what is the answer?
D.
B. Okay.
D.
D. Okay, yeah, the D is the correct answer, all of the above, right? So we had discussed about microfluidics systems in this course regularly. So now we know that how we can make a microfluidic channel using PDMS and glass. So we can make the channels in PDMS using soft lithography, and then we can bond the wafer on glass substrate, right? So these are we can make this to use in a lab setup to mimic biological system, and then we can control the fluid flow easily, because these are like small channels, and we can like control it using like different instruments we have very easily. And these are cheaper because these are very small, and we can make like a large batch in one go, and we don't need that much of material for that. Okay, so these are some advantages of microfluidics, and these are very useful for biological analysis, so that we don't have to do the experiments, the real experiments on human or on some patient or on some animal, which is like very cruel, right? We can mimic the biological systems using microfluidics, and that is the main advantage, that we don't have to go for testing any drug, testing any thing on animals. Okay, so these are the things we learned in week 1 and 2. What are the advantages of using sensor systems? What is microfluidics? What are microsystems? What are the different components in this course, in this sensor technology in general? Okay, so let's go to this next question. I'm just trying to save in between, because I write these things and then if I move, I have to save it. Okay, so in week 3 and 4, we mainly focused on microfabrication techniques. So first we learned about photolithography. So we know that there are multiple steps. So first step is the substrate. We will start with a clean substrate. So substrate cleaning is very important. Now we know that. Do you have any question, Priya? You can ask.
Ma'am, actually, whatever you are saying means whatever you are teaching about everything, gas sensor and everything, from this thing only they will ask question, right? Whatever you covered.
Actually, see, this is like a 1 hour extra session. So I'm just trying to give you a summary of everything, so that this will be useful for your exam, right? You,
Ma'am, in course layout, they have mentioned optical gas sensor and FET
yes,
gas sensor, everything they have covered. Means in this session, I didn't see anywhere about those things. So if they will ask or not, if they will ask, then I will study about that because I have to
they
clear
can
this
they
exam.
can ask like everything whatever they discussed in this 12 weeks course. I'm trying to squeeze the important things in like this live session, like in 1 hour extra session, right? So it is not possible to cover everything. I just briefly mentioned that the output of a sensor can be optical, so you
Hmm.
should learn these things like whatever they discussed. Obviously I have not included the Arduino part or console uh, simulation for today's class, right? I cannot include everything, but I have
Yeah.
tried to include in the live sessions, and whatever was discussed in the lecture videos, that you obviously have to like remember. Okay, but this is just for your reference, so that it's like a quick note or revision. You can think of that, like, okay, just before the exam you cannot read everything, right? You already remember these things, you have already watched this video, so this is just like a recap or the quick summary for that. Quick revision, just we used to do just before the exam. It's like that only. Okay,
Okay.
please like try to read everything. uh, they can ask any question.
Okay.
So this is one topic, photolithography, that we discussed multiple times, and I feel like it's a very important topic. There will be questions, because this is like, as Professor Wandi also mentioned, this is like the heart of microfabrication. If you know photolithography, then you know at least a bit about microfabrication. Okay, so that is why I'm going to again remind you that how the process looks like. So we will start with a clean substrate, because if our substrate is not clean, our photoresist coating will not be uniform, there will be dust particle, there will be uneven layer of photoresist, and our exposure will not be proper, our contact with the mask will not be proper. So it is very important. Okay, we can either go for solvent cleaning like using normal acetone and IPA, or if it's a silicon wafer, then we also do RCA1, RCA2 cleaning. The cleaning you will do, that depends on the structure, like final structure you are expecting. If you are expecting a very fine features, then you should maintain like a good protocol for that, so that you clean your substrate thoroughly. Okay, and after that, so this is the first step. What we do, we go for photoresist coating and soft bake. Okay, there may be another step like primer coating, we have discussed about that, to increase the adhesion, but I'm just describing the basic photolithography process. So this is the step 2. We will coat photoresist using a spin coater. We know what are the precautions we have to take during the spin coating. Okay, so that there is no air bubble, the uniform, the layer is uniform. Okay, the sides are uniform, at the edges photoresist thickness is uniform, right? We learned all these things. And after that, what we'll do, we will put the photo mask, and we will do alignment. Alignment is where, if there is already some structure in the in your substrate, or we are doing the multiple steps lithography, then alignment is required, so that our first layer features of the first litho and features of the second litho align properly. Okay, so we'll do that, and then we will do UV exposure. And after UV exposure, we do something called development. Okay, so development post baking is optional in many in case of many photoresist, but in case of some photoresist we may need these things. Okay, so this is like a general process flow for photolithography process. It can be slightly different depending on your photoresist and the process that is mentioned in the data sheet of the photoresist. Okay, and I encourage you to search for data sheet of a photoresist and how the process vary for different photoresist. So after development, what will happen, so we know that there is one positive photoresist and another is negative photoresist. In case of positive photoresist, the exposed portion will become soft and will dissolve in developer solution, and in case of negative photoresist, the exposed portion will become hard. Okay, and after that we can do like metal deposition, as you can see here, and that metal deposition will be uniform. And what we can do after that, we can go for polishing plus etching. So polishing will remove the top portion of the metal. Okay, so we will have things like this. So this is photoresist, this is metal, this is again photoresist, metal, photoresist. Okay, this will be after polishing. And after that we can go for etching. Okay, so polishing plus etching will give us something like this kind of a structure. It will remove the metal part, and then we can remove the basically like etch out, or typically we call it like the strip of process of photoresist. We can do it by using acetone. Okay, most photoresist, so these are polymers, they go away in acetone. Okay, so after that we will have a final structure of metal, which is like opposite for positive photoresist and negative photoresist if we use the same mask. Okay, and if we want to have the same pattern for positive as well as negative photoresist, we will use a different mask. Okay, so normally what we do, we try to keep our mask same, because making the mask again is like a time taking process, we cannot make it very easily. So we try to choose our photoresist in such a way that we get the final pattern as desired. Okay, now along with photolithography in week 3 and 4, we have also discussed about bulk and surface micromachining. Okay, so bulk and surface micromachining is like a removal of etching of some material. Okay, in case of bulk micromachining, we will remove most portion of the silicon wafer. So suppose this is silicon wafer, we will remove this portion of silicon, okay, significant portion of silicon. So that is why it's a bulk micro machining. And in case of surface micro machining, we will remove some portion at the top, okay. So at the surface. So these processes, micro machining in general, we need to make MEMS structure, for example like a cantilever, suspended beam, all these things. And because this course, a significant portion of the course is on MEMS based sensor, that is why we learned about bulk and surface micro machining in third and fourth week, okay. After that, we started few lab classes where we learned different clean room protocol. And mainly in one of the lecture videos in these weeks, we learned about biosafety hoods, okay. So there are different classes of biosafety hoods: class 1, class 2, and class 3, okay. Now we already know that what are the difference between these three classes. So in class 1, biosafety hoods, it protects the person and the environment, but not the product. What it means? It means that, you know what is the biosafety hood? It's like a closed kind of it looks like a film hood, but we mostly use to handle biological samples or biological sensors. So in class 1, it protects the person and as well as the environment, so that there is no no hazardous chemical. If we are handling some biological sample that can have certain disease, and we will try to do inside the wood in such a way that the sample will not affect me, the sample will not contaminate the environmental, like outside environment, normal air, okay. There is no escaping of any kind of hazardous gas or hazardous chemical from the sample outside, okay. But it does not protect the product. That means from outside environment, air can go inside, okay. In case of class 1, 2 and 3, it protects the person, it protects the environment, it protects the product as well. But the difference in class 2 and 3 is that there are certain filters inside this biosafety hoods that actually clean the air, and some portion of the air will be exhausted and some portion will be reused. So in class 3, the safety is highest, and that means it will not reuse much air, like after filtration it will exhaust, and like it will use new air for circulation. And in case of class 2, I don't remember the exact percentage, some portion of the air after filtration will be reused, okay. So you can check the different types of, you should check the different types, what are the advantages of using like these classes of, like different classes of biosafety hoods, and what are the differences, okay. If you don't remember it right now, maybe you can go through the lecture videos and the lab classes a few more times, okay. So these are the things we learned in week 3 and 4. So the question is, so this I have earlier also discussed in the class, just want to remind you this based on the content of week 2 and 3 and 4. So what are the key concepts of, the question is, what are the key concepts about MEMS that we discussed in the class, okay. So this question actually summarizes like whatever the things that we discussed in in these 4 weeks. So I have already discussed. If you don't remember it, I will write it down again, okay. So first thing that we know that MEMS systems are made up of, so what are the things? There are 4 components in a MEMS systems. What are these?
Microsensor, microactuator,
Micro, yes, microelectronics, and microstructures like microchannels. Okay, so microsensors, microactuators, microelectronics, and microstructures. So these are the components of the thing that I discussed in the first slide. So in a sensor system, what we have sensors, we have actuators, we have decision making unit, that will be the microelectronics part, some kind of chip will be there. Okay, and then for connections and other peripheral, as other peripheral unit, will have microstructures. Then the second point was the fabrication. So it involves deposition, patterning, and etching. Okay, these three things mainly, and doping sometimes, because we have also discussed about doping like boron doping, but these are the things that as I am just giving you this slides as per the like lecture videos. So there Professor Pandya has mentioned that these are the main components of fabrication of MEMS system. And then next point was so we have also discussed about in etching, we have discussed about dry etching and wet etching. Okay, wet etching is like etching using chemicals. Okay, so that etching is highly selective, and the rate of etching is very fast. And we also learned that in case of dry etching, the etching is directional, whereas wet etching is selective, right? So chemical etching is popular mainly in for MEMS systems, because we have just seen that in case of MEMS we go for bulk micromachining to make cantilever kind of structure. For that we have to etch out like a significant portion of the wafer, and that is why we mainly prefer chemical etching that generally has a higher etching rate compared to dry etching. Okay, so that was the third point. Chemical etching is popular as it has higher etching rate. Okay, then next point was there are three types of mainly pressure sensors. Okay, in MEMS that we have discussed multiple times. Okay, pressure sensors we learned that we can use it as a biological sensor. That is what we are discussing in last few weeks. And the pressure sensors can be capacitive type, piezoelectric type, or piezoresistive type, kind of similar, like it basically the electrical property changes, and thermal. Okay, so these things we have studied. And then there are three types of actuators, MEMS actuators, mostly three types that we have learned. That is thermal, that uses the thermal expansion of material to move something. Okay, and then capacitive, and then piezoelectric, transducer. Okay. And then so 1 2 3 4 5 6 pointers, we have also learned about the benefits of MEMS, so which are speed, because these are smaller. Okay, size is also compact, and power consumption, which is like the important thing when we are considering about IoT systems that require like many sensors. Okay, right. So these are the things we learn. Next, let's go to week 5 and 6. So I'll not explain much these things. So in week 5 and 6, first we learned the different types of silicon substrates. So by looking at the primary flat and secondary flat, so the primary flat is the bigger flat one, so this one, and the secondary flat is the smaller one, and based on the location we can decide what is the type of the silicon wafer, and what we have learned that whether it is a 111p type, 111n type, 100p type, or 100n type. Okay, then we have also learned about silicon dioxide as an insulating layer. We know that it's a very good insulator, so we often use it. We often use silicon as a substrate, we often use SiO2 as an insulating layer because of its properties, because it provides great insulation. So electrically the conductivity is very low, and then it has very good thermal stability and chemical stability. We already know what can etch SiO2, it is mostly stable chemically. Okay, so we know the chemistry, like how it works, and then it is very easy to grow or deposit. So I have discussed about these two terms, like growth and deposition. Deposition is like we will deposit material from target material on top of a substrate, whereas we will grow the material from the substrate itself. So if we grow silicon dioxide on silicon, then some portion of silicon will be consumed in that total SiO2 thickness, whereas in case of deposition of SiO2, we will deposit SiO2 from say some target using sputtering. So silicon will be same silicon, and we can deposit SiO2 on other substrate as well, where we will grow silicon on SiO2 on silicon substrate. Okay, so these are the things we learn, and we know that SiO2 is optically transparent and it's mechanically very stable, and that's why we use this as a insulating layer in our MEM structures. We have also discussed about these three types of PVD technique: thermal evaporation, E-beam evaporation, and sputtering. Okay. Next, we learned there was one class on signal conditioning unit. So signal conditioning unit, so as I mentioned, that often the sensor output will not be sufficient to use directly in a system. So what we do, we often amplify the signal, output signal. We reduce the noise. So for that we now sometimes use filters. Okay, so in this course, in one class we only learned about the amplification. Filters, you already know what filters does. So I will focus on the signal conditioning circuit, mainly the amplifiers that we have already discussed. We can amplify a signal using operational amplifier, op-amp. It can have like two configuration: inverting configuration and non-inverting configuration. So if it is a non-inverting amplifier, okay, so how this circuit diagram will be, we will provide input to the non-inverting terminal. So this is our V in, and we will give the feedback here. So this is will be our feedback resistor. We can denote it using R2, and this will be our another that resistor, that is R1, and this is our V output. And we know the relation in case of non-inverting amplifier. The relation is 1 plus R2 by R1 multiplied by V in. So this is our gain, right? Similarly, we can have an inverting amplifier also. So how that will be, the circuit diagram will be. So how we can get this V out expression, that we have already learned in the live sessions, that we can use KCL and KVL to solve this circuit, and we can finally get the output voltage. Okay. And in case of inverting amplifier, we will provide the inputs to these inverting terminals. Non-inverting terminal will be ground, so we'll provide in V in here. This is our R1, and we obviously have feedback because it's a op-amp. We want our output to be not saturated, so that's why we provide negative feedback. And in this case, our V out will be minus R2 by R1, right, into V in. So in this case we get an inverted output, but we can again make it like a plus positive sign, same as the input, by again using another inverting amplifier that has a gain of 1. That means RO if R1 and R2 are same. So this is an amplifier circuit we often use after the sensor to amplify the sensor output if our sensor output is not enough. But again, if our sensor output has some noise, amplifier will amplify everything. So often we use also filter along with it, right? Next, in week 7 and 8, we discussed thoroughly about e-beam evaporation and sputtering. So in e-beam evaporation, what we use electron beam. So there will be one filament. There we will apply enough energy so that electron get ejected, and this electron will be directed towards the source material by using magnetic field. We know that electrons will be deflected by magnetic field, right? And we will because of this energy, electron energy, the source material will become melt, and it will go to its molten state and then will evaporate. That will go to its vapor phase and will deposit on the substrate holder on the wafer that is connected to this substrate holder. Okay, we also learned about this quartz crystal monitoring device that can monitor the thickness of the film deposited, and as soon as we know that we have achieved the desired thickness, we can turn off this electron beam and this deposition by placing the shutter in front of the source. Okay, so no deposition will be there on the wafer. It will be some deposition at the shutter. Okay, we also learned about sputtering, how we use argon gas to sputter element. Okay, if it's a very light element, light material, then we will use a different inert gas. Okay, and if it's a heavier element, we will use another heavier inert gas, okay, for effective sputtering. We also discussed oxygen plasma system. What are the components? I will not go through it again, and please go through it. It's an interesting system that we use for wafer bonding, right? Then we also discussed about shape memory alloy. If you can remember, shape memory alloy, we discussed about nitinol. So it is a combination of, it's an alloy of nickel and titanium, right? It has so whatever it's the nitinol has, like it will have some shape, and whatever its shape at higher temperature, it remembers that. Okay, so that phase transition temperature, so basically it has two phase. One is low temperature, so which is martensite phase, and one is high temperature, that is austenite phase, right? So it remembers the high temperature phase. So as soon as the phase transition temperature, the temperature reaches the phase transition temperature, it will go back to its original shape. Okay, that's very interesting, and we can use it for actuation purpose. We can use an ethanol wire for actuation. Okay, and the phase transition temperature, it will have a range. The range was, I think, minus 50 to around 100 degrees Celsius, and based on the combination of composition of nickel and titanium, we can shift the transition temperature, and many times it is kept as 37 degrees Celsius, which is the temperature of a human being, if we want to use it for biological applications. Okay. So let me quickly go to the next last week content, and maybe we can take a question. So in last week, what we discussed about the clean room classifications. So I have given the definition here for your reference. There are two types of classification: ISO standard and FED classroom standard. So we should remember both of this. The figure is given in the lecture notes. After that, we also learned about actuator, like which is a stepper motor. We learned like there is two components in a stepper motor. First one is the stator, okay, which is stationary, and another one is the rotor. So rotor is normally a permanent magnet, but depending on the type of the stepper motor, it can be different also. So stator is like a coil or winding. So when we apply current to this winding, we know that current carrying conductor will create the magnetic field, and say because of the current applied to these two coils, so this becomes say south pole and this become north pole. So this magnet will align here because opposite poles will attract, and then we will change the current and will make this as south pole and this as north pole in the next turn, and then this magnet will come to this side. Okay, so this will move in this direction. So alternatively, if we apply current to this coil, so then the permanent magnet will move to this direction, and then that's how we can achieve the rotation. Okay, so we learned about that. We learned about the step size. If I hope that you remember the formula how we can calculate the step size. Okay. Then we learned about breast cancer analysis using mechanical and electrical properties. I will not go through this much because we are still learning these things. We have discussed in last week as well. Okay, we will be discussing in the next live session as well, because this is the topic that we are discussing recently. Basically, the point is that by measuring electrical and mechanical properties using a MEMS system, we can make a sensor for breast cancer analysis that can be helpful to analyze to enable early detection. Remember that we often use these sensors along with other traditional methods because in case of breast cancer, sometimes the biopsy can result like triple negative. It might show triple negative, but it is like a definite it is a breast cancer case, right? So sometimes the traditional methods may not work. So in that case, we use like a multiple methods to verify to multiple methods of diagnosis, and sensing or sensor technology can be one component of that. Okay, it is not enough to identify everything. Okay, but then we still use it to minimize any error. Okay, because these are very important. It can save someone's life. Okay, so we have maybe some time. We can take one question, like a small question. So this is based on this week 7 and 8 content. So this is a very general question. You should remember this. I'm just giving you this question. So which factors influence the thickness of photoresist layer? Because we have discussed about photolithography in this course so many times, so that is why I thought of giving this question. Like, what are the factors that determines the thickness of photoresist layer while doing spin coating? Okay, do you remember this?
Speed
Yes, the
or
rotation speed.
viscosity, the viscosity of photoresist material,
Yes, and also
and
about duration, right?
and spin coating time also,
Time, yeah,
how much time it is taking.
right. So these are the main factors. So first factor is the most important one, is the viscosity, because like even if you keep constant the speed and the duration, if it's the photoresist is kind of like a very liquidy, it has a very liquidy consistency, then it will spread out more and the thickness will be less. Okay. And if it's a very thick photoresist, the it will not spread out that easily and the thickness will also be very high. Okay. So that is the most important parameter, most important factor that decides the photoresist thickness. Okay. So viscosity of photoresist. Next is spin speed, and then last one is spin duration. So I have also mentioned earlier in photoresist data sheet you will find this. So this x axis will be spin duration. Okay. That will be given like spin speed, it will be given in rpm, rotation per minute, and then this will be photoresist thickness, y axis. Say this is for a certain duration. Okay. And oftentimes this thickness, this graph will be something like this, it will saturate almost very high speed. Okay. So viscosity is the key point here. And you can decide, suppose you are setting this rpm speed as 5000 rpm, then what is the expected thickness, you can get it from this data sheet, photoresist data sheet. Okay. This will be usually in micrometer. We normally deposit photoresist layer or spin coat photoresist layer in some micrometer. Okay. Again, it depends on the feature, the final feature you are expecting. If your feature sizes are big and you don't care much about precision, then maybe you can keep a very thick layer. But to make very fine structure, we often go for thinner photoresist. You know why? Because if your photoresist will be very thick, say you will have a mask here, photo mask here, some portion will be dark and some portion will be light. If it's very thick, there may be some leakage at the edges also. Okay. uh, because the photoresist will not be completely opaque, and there may be some leakage also, and the final feature size may not be exactly same as you desire. Okay. So for that case, we often use a very thin photoresist layer that can give us fine features. The contact will be proper with the mask, and whatever the features we will have at the mask, that will be transferred to the photoresist layer. Okay. So these are the things that we have studied. I think we almost have time, so I try to give an overview of all the contents of the all the wheels. I have excluded few topics. I feel like these are some important topics. That's why I have included. But please go through everything that those were discussed in the class. For the last week, I have not discussed week 12 that we will be discussing next Tuesday, and we have not also. Yes, Priya, if you have any question.
Ma'am, in CVD, too many variants are given in the syllabus. Should I read everything, whatever they have given, like types?
So try to remember, try to find out the similarities and different differences between the every type of CVD. So PCVD you should definitely know, because that is like one topic. Okay. And with respect to that, what are the advantages and disadvantages of other techniques, that you should know. In general, like when we learn microfabrication, we have this chart, like different types of CVDs and advantages and disadvantages, basically a comparison. So at least you should remember the comparison of different types of CVDs. Okay. And where you
Okay.
can use it. Yeah, because this comparison is important. See, as I mentioned, LPCVD, which is like low pressure CVD, right? But you should know what low pressure means there, because in case of sputtering and evaporation, we do like we create very high vacuum. Okay, that is normally like 10 to the power minus 7 minus 6 millibar. Whereas LPCVD, even though it's a low pressure CVD, it's not that low. Okay, so few numbers you should know. Again, that what is the like temperature difference in case of, suppose if you are doing APCVD, normal CVD, atmospheric pressure, and if you are doing PECVD. Say APCVD we are doing at 1000 degrees Celsius. Typically, this is the range. Whereas LPCVD we will do at 200 degrees Celsius, right? So these things you should definitely deny. Okay.
Okay, ma'am.
So, is there any doubt? Any other doubt?
No, ma'am.
Okay. So then maybe we will stop the session here. Please go through the notes. I will provide this, and I hope that this will be useful for your exam. Okay. So see you in next class on next Tuesday for the final live session. Thank you for attending the session.
Thank you, ma'am.